У меня написано по-английски.
Я говорю, как хочешь.
Как хочу. Нет, тогда по-русски, конечно.
Давайте тогда по-русски. По-русски. А написано пусть будет по-английски, неважно.
Да, я уж не буду переписывать, Саша.
Нет, но с одним условием, что если кто-то все-таки появится англоговорящий, то мы перейдем.
Ну, дайте знать, да.
Я тогда скажу.
Да, хорошо.
Или кто-то-нибудь мне скиньте тогда, если я не хочу все время смотреть за участником. Но пока вроде бы я никого не вижу. Нет, есть. Ну что, ладно, тогда на английский. На английский. Все. Okay. Welcome everyone to our first seminar this year. Our speaker is Sasha Bobenko. Okay, your floor. Please.
Okay. Well, I'm very glad to be in Skolkovo, or at least virtually. I'm glad to be with you. And my talk today will be on discretization of confocal quadrics. So I will just share my screen. So, okay. So do you see the screen? Please confirm. Yeah.
Yeah.
Yes.
Okay, good. So so I will. The talk is based on several papers, and the main topic was discretization of quadrics, and in particular of confocal quadrics. And these discretizations and these quadrics will appear in various forms. So in my talk, I will jump from topic to topic, but I will warn you before I will make this jump. So it is related to geometry, of course. It is related to integrable systems, and some new geometries in circular nets will appear also. Yeah. So let me start with a picture of an ellipsoid, and the lines you see here is a conformal parametrization of ellipsoid. It's known that this ellipsoid, an ellipsoid can be conformally parametrized by its curvature lines. So what you see here is a conformal curvature line parametrizations. The lines are curvature lines, and they split your surface into infinitesimal squares. Yeah. In this picture, you see that the squares are not infinitesimal, but they look like squares. Okay, and the question is, how should we define something like this as a polyhedron in such a way that most of the properties are preserved? Of course, it's not precise formulation of the problem. It depends on which properties would we like to preserve, and there are various options. But all of us know that, confocal quadrics, ellipsoids are related with a lot of mathematics, are important for introducing some curvilinear coordinates, or for separation of variables in Laplace operator, and so on and so on. So we would like to find a discrete version of this. So the problem is non-trivial. So I will present you, for example, a version of a discretization which we have found numerically, which is absolutely reasonable, and which we don't have yet theoretically. So you see, that's an ellipsoid. The faces are quadrilaterals, and they are all planar. There are inscribed circles, and the circles, almost touch at the same points. Yeah. So, but it's not exactly the case that they have the same touching points. And you see that the combinatorics is inherited by the curvature lines. So there are some distinguished points here, these are the points where both curvatures, both principal curvatures coincide. These points are called umbilic points. So again, the pattern is like in the...
Sasha,
yeah?
Is this picture it's numerical finding?
It is numerical. It is numerical. Yeah. So, well, we hope there is some theory behind this, and we are working on this. But what I will present you will look differently. Yeah. So I'm saying that possibly it's not a unique discretization, which is structure preserving. Maybe there are more, but more research should be done here. Okay, so
there is no reason to believe that there is only one species.
Yeah. So I will explain you this picture. You see, it's a lot of sort of more complicated, and this picture shows us confocal quadrics that were discretized. And also, amazingly, we will see also such pictures, which look completely different, pictures with inscribed circles, and these pictures also are discretizations of conics and of confocal conics. So these are so-called incircular nets or IC nets. Okay, so that was an introduction. And now, well, that's the list of papers. There are several papers devoted to this with various co-authors. So, and some of them are quite recent, exist only as preference. So therefore, it's written 2021 plus. Okay, I will present results from there. But let me start smoothly from some basics, yeah, about confocal quadrics. So first of all, let us define them. So you have n numbers that are ordered. A1 is greater than an and so on. And a parameter lambda. And then this formula you see here defines us one parameter family of quadrics. It's a surface in n-dimensional space, hypersurface in n-dimensional space, and it is known as a family of confocal quadrics in Rn. So two examples you see here are confocal quadrics in dimension 2 and confocal quadrics in dimension 3. In dimension 2, all the curves you see here, they have the same focal points, all these ellipses and all these hyperbolas. And one important property you see here is the orthogonal intersection. Hyperbolas intersect ellipses orthogonally. So you have an orthogonal coordinate system in the plane. So it's a generalization, if you want, of polar coordinates or of, I don't know, in 3 dimensions of cylindrical and of spherical coordinates. Yeah, but that's the way how confocal coordinates are also defined. So important property, orthogonal intersection. The same is true.
Sash,
yeah.
Excuse me. In dimension 2, when you have ellipses and hyperbolas,
yeah.
So ellipses are for positive lambda, hyperbolas for in between A1 and...
Yeah, you have two A's, A1 and A2, and there are 3 intervals on the real line determined by these 2 numbers. Yeah. So in one interval, if lambda lies in one interval, then it's just empty set. Yeah. So because the right hand, well, the right hand side is negative, right? So in one interval you get hyperbola, and in another one you get ellipse.
And what about complexification of this picture?
Well, you can, of course, complexify and play the same game in the complex projectives, in the complex space, yeah? And you can define confocal quadrics exactly in the same way, just by these formulas. So, I mean, confocal is a sort of, sort of complicated notion, yeah? So, but when you consider dual quadrics, then the coefficients become 1 over, yeah? And then this means that the dual quadrics build a pencil, a linear space of quadrics. And the dual quadrics are just the quadrics that are defined by tangent hyperplanes, or in the two-dimensional space by tangent lines to these quadrics. Yeah? So in the complex case, same formulas. So, but look at the case dimension 3. Look at this red point. It's an arbitrary point in space, in three-dimensional space. And through each point, there are exactly 3 quadrics, 3 confocal quadrics from this confocal family. These 3 quadrics intersect orthogonally, and they have different signatures. Okay, maybe this is a little bit better formulated here. So let us introduce confocal elliptic coordinates. So through each point in our n-dimensional space, which is not in the coordinate hyperplanes, they pass exactly n orthogonal quadrics. That's what we have seen in the cases of dimension 2 and 3. So these quadrics, they have different signatures. And of course, they correspond to some values of lambda equal to u1, un. Yeah? And these u's you obtain when you solve these equations for quadrics written here in the middle. Yeah. So do you see my mouse?
Yes.
Yeah. Okay. So you solve these equations, and u, if u is fixed, then the surface is fixed. And you see these u's, they lie in the corresponding intervals. Yeah. So there are exactly n orthogonal quadrics. And this is the way how you can introduce so-called confocal or elliptic coordinates. So given u's, you can recover your x. There is a map from u's to x. There is an explicit formula for x, of course, for x squared, because it's symmetric, in terms of these u's. Well, you can easily recover this formula from the system which is written here above by just computing the corresponding residues here. Yeah, this will be an important formula for us. You see, xk, all the coordinates. So given n coordinates ui, these are the coordinates in these intervals between a's, you have the formula for x's. Actually for x squared, so you should take the square roots. And this is these are confocal coordinates. U's are confocal coordinates. So the question is how to discretize these formulas, how to discretize this geometry. Okay, there are of course many ways, and let me explain you how to do this. So, but before I do this, let me make my first jump, and I will show you how confocal quadrics and confocal conics in this case appear geometrically in completely different context. But at the end of the day, we will these things will come together. Yeah. So this is a circle in the plane. So we have a picture in the plane, and now these are 4 tangent lines. So the lines look parallel, but you will see that they are not. They are almost parallel. They are 4 arbitrary lines. Now we build here 4 additional circles. They are, of course, uniquely determined as soon as the lines are fixed. Yeah? Now we have a 1-parameter family for this circle. Let us take this one. But as soon as this circle is fixed, we have these 2 tangent lines that are also fixed. Now we have these 2 corners where the circles are fixed. Now we have these 2 lines. And now we have a quadrilateral. and the first incidence theorem. So it doesn't matter how do we choose these lines, how do we choose these circles. If 8 circles exist, then this 9th quadrilateral built by tangent lines also has an inscribed circle. So, okay. I will explain later maybe how one can prove such things. Yeah. So what are the basic tools here? So now let us make this smaller and proceed. Yeah. So these circles are uniquely determined. So now these lines are also uniquely determined. Now we are already using this 3 times 3 incidence theorem to show that the lines exist. Now we are using this theorem a couple of more times. Then these circles exist, and so on. Yeah. So these circles exist, these lines exist, these circles exist, these circles exist. Now you see already that the lines are not parallel, or they don't have to be parallel. And that's how the picture grows.
Sasha.
Yeah.
There was only one parameter from the beginning, right?
Well, there are more parameters, yeah. So from the very beginning, you have chosen a circle and then 4 lines. These 4 lines are arbitrary.
Mm-hmm.
And
no.
after that,
besides of in the initial step, there was also a circle you inscribed in the corner, and the radius was arbitrary.
Yeah, exactly, yeah.
And there is no more parameters.
No more parameters, yeah. So it's finite dimensional. I don't remember how many parameters do you have here. Maybe it's something like 5 or 4. Yeah, but as soon as you have fixed these parameters at the beginning, you see the further development, the further extension is unique. Yeah. Okay. Okay. Now, first result is the following. You can prove that all the lines we have constructed are tangent to some conic. This is this conic alpha shown in red here with its 2 focal points you see in this picture. So I will not give you precise proofs, but I will give you the main tool for this proof a little bit later. Yeah. So just first let me formulate the result. Okay. Now next thing is that if you consider the points that lie on combinatorial diagonal lines, these intersection points of the lines that are combinatorially diagonal on this IC net, they lie on conics confocal with this conic alpha we have defined in the previous slide. Yeah. So here we have our conic, and all the conics here are confocal. You see they are in 2 families, of course, horizontal and vertical, and these are exactly these ellipses and hyperbolas. Mm-hmm. So that's the picture with these confocal conics. Yeah. So this is our original conic. All the lines are tangent to this conic, and now we have a family of these green conics that run diagonally, and these green conics that also run diagonally. So they are confocal conics. So you see that in a way, this discrete picture we are constructing by drawing circles. Yeah.
How do you connect diagonal? Is it straight lines, or is it smoothing needed to get?
No. The claim is that you just consider the intersection points of lines, and these intersection points of lines lie on confocal conics.
Okay.
Yeah. So what, and you see this, yeah, in this picture. Okay, it's not an interpolation. Okay, now you see what you can do. You can build even closed periodic pictures like Poncelet construction, and again in this picture you see the images of confocal conics. So all circles here have different radii. Now the main tool, yeah. So how one can prove this? It's rather elementary as soon as you know this theorem. It's a classical theorem which you can find in Darbur book. Darbur finds this theorem fascinating, and the theorem says that in this picture which you see here, you have 4 lines that are tangent to a conic. This conic is shown in black. And 3 claims are equivalent. So this quadrilateral built by these 4 lines has an inscribed circle. And this happens if and only if the 2 opposite points of our quadrilateral, T and Y, lie on the conic which is confocal to this black conic. I remind you that the black conic was defined as the one which is touched by all the lines. Of course, you have one parameter family of confocal conics, yeah, and then there exists a confocal conic that goes through the point Y. But the claim is that if this quadrilateral has an inscribed circle, then this conic passes through the point T as well. And the same is true with another pair of points, X and Z. Yeah. And actually what is not written here, but it's also true that for 2 other points, yeah, so which are the 2 points that are the closest, the intersection points of the lines that are closest to our tangent conic, they also lie on the tangent conic. So actually there are not only 3, but not only 2, but 4 conics. Sorry, not only 2, but 3 confocal conics passing through the intersection points of these 4 lines. Okay, so this is so-called Grave-Schall theorem, classical one, and it's amazing that it relates confocal conics with circles, with inscribed circles. Okay, now we come back to our algebra, and I write down the formulas for the coordinates which we already had. So these were formulas for confocal coordinates. I remind you that we had these u coordinates, and there was a formula for xk squared. This is our Euclidean coordinate. Now it's already without square, and therefore there are square roots here. So this term in the denominator contains n terms because there are n different a's, and since this and only one well, I'm sorry, n different u's here, and only one a. And since these u's lie in the gaps between a's, the sign should be chosen in a way that all the square roots are positive. And here it's just an expression in terms of a's. So this explicit formula for the coordinate functions xk will be not that important for us. What will be important for us is the structure of this formula. And we see that what we have here is a product in the denominator, is the product of functions of one variable. xk is a function of n variables, u1, u2, and so on, un. But it is a function of a product. It's a product of functions of one variable. So these functions are also known, they are square roots, but this will be not that important for us. So there is this factorization property, that we have this factorization property for confocal coordinates. And another property, which I mentioned already a couple of times, is that these coordinates are orthogonal. This means if you differentiate x with respect to a couple of u's, there will be 2 orthogonal vectors. So this means that all hypersurfaces intersect at the point xk orthogonally. So two important properties. And now an important step in this consideration is this claim, which we were not able to find in the classical literature. Yeah? So these properties are characteristic. So if you are looking for orthogonal coordinate systems in n-dimensional space with this factorization property, then it must be the system of confocal quadrics. It's confocal coordinate system. So in principle, you can derive these formulas, which are written here, from these two properties. Okay. So, and that's the way how we discretize. So we say we would like to consider a discrete system, which is orthogonal and which is factorizable. Okay, but first of all, look, so if we do this naive discretization and say, okay, now instead of continuous function, we have discrete function and it determines us some lattice, and in this way, it should be in this way, it should be a lattice which is combinatorially cubical lattice, and we have orthogonal intersection everywhere, but then there is no room for research. Yeah, so it will be just straight line, straight hyperplane hypersurfaces, and that's it. So therefore, the orthogonality condition that we are implementing here is a little bit more tricky, but it's also natural. Yeah, so we leave a little bit more freedom here. So we say that, first of all, it's more convenient to consider a net, which is defined on the n-dimensional lattice with half integer coordinates. So because it will be useful for us to deal with two sublattices. So it is called orthogonal if for each edge, look at this picture, that's the edge xn to xn plus ek. This is one of the vectors in Z. We have 2 to the n minus 1 vertices in the dual facet. So this picture in the three-dimensional case, we go 1/2 step in the direction of ek, and then look at all vertices that lie in this hyperplane. And in the three-dimensional case, we end up with 4 vertices. You see the last coordinate is always plus 1/2 of ek. But in two other directions, ei and ej, we have all 4 variations of signs. So there are these four vertices. So, and the condition is that all these vertices, they must lie in one hyperplane. In the three-dimensional case, this means that these 4 vertices are coplanar, and moreover, this plane is orthogonal to this vector we have started with. And that's the orthogonality condition we would like to implement. So it happens everywhere on our orthogonal, on our coordinate system, and that's what we call a discrete orthogonality. So I think it's a new notion of discrete orthogonality, and of course it's worth to investigate it in more general setup. And then a definition is a discrete confocal coordinate system is a map from these letters to Rn satisfying 2 conditions. First, it is factorized exactly in the same sense as our continuous system was factorized. Now, our parameters are discrete, and 1 and 2 and so on. They are integer, and all the coordinates formulas should be products of functions of one variable. And the second condition that X is orthogonal exactly in the sense I have explained to you previously. Yeah? So that's the definition. And of course, the next step is the theorem.
Sasha, it's not obvious at all that this set is not empty, right? Because you need to satisfy factorization plus orthogonality.
Yeah, of course it's not obvious, but if you just look a little bit and more carefully on this, then it's easy to convince yourself that it's not empty. Moreover, you can I will give you an explicit description, a complete description of this set. Yeah. So in principle, it's not obvious. So, and of course, yeah, we tried many ways to find various discretizations, and this orthogonality condition appeared actually a little bit later, and I don't tell you the whole story, because what we did first, we have started, of course, with an integrable system, and then we were trying to discretize it, and then came to this setup of factorizable coordinates and to this orthogonality condition. I will mention the system a little bit later. Yeah. Okay. So first, let us stay with algebra and with geometry. So we have this theorem. So discrete confocal coordinate systems, as they were defined in the previous slide, they exist n real numbers. You remember we had these n real numbers in the continuous case. And n real valued functions. So of course you can treat these u's now as functions of discrete variable n. But it will be convenient for me to build in reparametrizations, and therefore I'm not saying that this function is just our discrete variable. I would like to have this reparametrization freedom and say, okay, I am considering a function of one discrete variable. Yeah, so we have these real valued functions u's such that the following equations are satisfied for any integer n and for any sigma. Sigma is just a shift in one of these n directions. So okay, these are the governing equations. X at the point n, and then we shift it to a half integer variable, half integer shift, and we have the following formula. So I remind you that in the continuous case, instead of this product, we simply had x squared. So, but of course, if you refine your discretization letters, then these two values go to the same limit. And the factors, the denominator was the same as in the continuous case. So, and now again, by computing the residues, we can invert this formula and write down the formula for the coordinates xk in terms of these discrete functions uj. And that's the formula. So you see, again, in the continuous case, we had the formula for x squared. Now it's the formula for this product. And so it's an iteration formula which allows us to compute one x after another, and not just the formula, the final formula for one x. Okay, so, actually it's not that difficult to prove this theorem. The proof is more or less parallel, also not quite trivial, to the continuous case, where you prove this theorem that factorizable and orthogonal imply the confocal coordinate systems. Okay, and now we come to the following parametrization formulas. So now there are formulas. So that for discrete confocal coordinate systems, there exist some functions, fk, functions of one variable, and the coordinates functions are recovered in the following way. You have a product here, and these functions satisfy these iteration conditions. So the products of f's at two adjacent vertices are exactly our discrete parameter functions we are working with. Okay. So, okay. So I had some computer warning here. Can you see me? Yeah. Can you hear me? Yeah. Okay.
Yes, that's
okay, good.
Yes.
And now look, what should we do? Given a sequence of these functions u, j, which are arbitrary reparameterization functions of nj. In particular, you can take uj is equal to nj. It's just your discrete variable, but it will be convenient for me to have this freedom. This equation defines the functions uniquely by prescribing their values at one point. You prescribe at one point, and then you iterate and iterate, yeah? And you get them all. And as soon as you have all these functions f, you have the formula for their coordinate functions. Yeah, so in a way it's explicit, yeah, and you see all the freedoms we have. Okay, now the relation to integrable systems. So if you use as variables without further reparameterization, I mentioned this already a couple of times, you just take these discrete variables, then, well, Laplace, delta, it's not Laplace, shift in the j direction, shift in the I direction of xk, yeah, so that's this hyperbolic Laplace operator is equal to this coefficient where you have n's in the denominator, and epsilons are not so important, they're just fixed parameters. And here, the differences of our coordinate functions in the j direction and in the I direction. This is so-called the discrete Euler-Poisson-Darbur equation with a coefficient gamma equal to 1/2. Well, first, I think it was considered by Konopelchenko and Shift. And we used first in our first paper to define discrete conformal coordinates in terms of gamma functions. So by solving this equation, and that was the starting point, how we came to all this construction. But now it's geometric construction, and I have explained you a geometric definition for everything. Yeah. Yeah.
Such, but there are much more solutions to this equation than you just constructed, right? So that's a question.
So whether all solutions of this equation are discrete quadrics, yeah? Discrete confocal quadrics, yeah?
I don't think so, but...
I'm not sure, yeah.
Mm-hmm.
So I don't remember, yeah. So maybe, yeah. So I don't remember, yeah. So one should check this. Yeah. Maybe
because it will be very strange, because your confocal discrete system of coordinates is based on factorization properties. It's not clear that factorization is needed for solutions of this.
Yeah, I think you are right. Yeah, so because it's multidimensional system. Yeah, so if you assume that x is factorizable here, then maybe it's
under the assumption that it is factorizable, then probably we will
factorizable solutions of this equation. Yeah, I think so. Yeah, exactly. Okay, now. Next slide, I will show you a couple of images now. N equal to 2, confocal conics, let us look what is going on. So these are the formulas in the smooth case. X and Y are given in terms of functions g of variable f and g of one variable, u and v, and they are satisfied. They're satisfying these quadratic equations. And in the discrete setup, you get exactly the same formulas, but instead of the equations for the squares, we have the equations for the products. You can solve all this. And in the smooth case, that's the classical formula in terms of trigonometric functions. And in a discrete case, the formula is similar, so but with some discretization parameters delta 1 and delta 2. And that's the picture, how this discrete confocal conics look like. So here all the edges are straight and all the vertices are well defined. There is no interpolation. So these are discrete hyperbolas and discrete ellipses as they come from this analytic construction or from this geometric definition with factorizable functions. And okay, so that was the case when we have chosen these reparameterization functions in the most natural way. We were discretizing cosine u and sine u. So you see, we have just replaced u by delta 1 and 1. We have this option of reparametrization. And this is, of course, important because when you discretize, well, this reparametrization doesn't mean anything in the smooth case, maybe, but it means a lot in the discrete case. You get different discrete lines. And moreover, so by choosing these discretization, reparameterization functions in a different way, you come to incircular nets. Namely, let me show you these lattices, these formulas, yeah. So here we are free to choose the formulas, solutions F and G, satisfying these conditions. As soon as we have chosen them, then we have a discrete system. So you can define, you can choose them differently and obtain the following constraint, satisfy the following constraints. In this case, you get solutions in elliptic functions. These are the same confocal conics, confocal quadrics, but different parametrization. And that's the way how these IC nets appear in this setup. So it's a special case of these formulas. It's not surprising because it turns out that also in the continuous case, you can introduce our confocal coordinates S1 and S2 in this case in such a way that S1 plus S2 and S1 minus S2, when they are constant, then you get straight lines. So you see, one conic here is determined by the condition S1 is constant. Another conic, confocal one, is determined by the condition that S2 is constant. Yeah. So, and there are, in addition, some special lines that are determined by the conditions S1 plus S2 constant or S1 minus S2 is constant. Yeah. So that's, of course, a very special parametrization, and this is the parametrization which is discretized in this case. Okay, now the case n equal to 3. We have, as I said, we have this half integer lattice, and the orthogonality condition I've described you can see clearly in this picture. So I told you that there are facets of our surfaces, and they are orthogonally intersected by the edges, which are in a way combinatorially dual to this. Yeah. So, and here you clearly see this orthogonality of the corresponding surfaces in the three-dimensional case. Yeah. And here again, three confocal quadrics and their discrete counterparts in the smooth and in the discrete way, in the discrete cases. So you see they look quite similarly. And the formulas are also, well, quite parallel. these are the formulas in elliptic functions for the three-dimensional smooth case in terms of Jacobi elliptic functions. Now our parameters are u, v, and w. These are three confocal coordinates. So, and that's a three-dimensional vector in Euclidean free space. And in the discrete case, the corresponding formulas are slightly more complicated, but essentially we have these discretization parameters, delta, delta tilde, and delta hat. And the discrete parameters are n1, n2, and n3. And that's the final formula for this.
May I ask you just
yeah, sure.
a little bit side question. In continuous case, confocal quadrics or conics, they're equivalent to Neumann system. What is the discrete version of Neumann system in the discrete case? Is the discrete system equivalent to your discrete parametrization?
I don't know that. Yeah, so I don't see Neumann system here. Yeah. So in this discrete case.
But you know that quadrics confocal is related to.
Yeah, yeah. So, well, that's of course a very good question, and there are well, we tried many different ways. Yeah. So how to discretize it? So you have many possibilities to characterize confocal quadrics. So, for example, yeah. So it's triply orthogonal coordinate system, and all surfaces, all hypersurfaces, all coordinate hypersurfaces are quadrics. And it's known that quadrics, well, they intersect along the common curvature lines. And curvature lines provide you with curvature line conformal parametrization, which is an isothermic parametrization. So in principle, you have three systems of isothermic surfaces. So we thought originally we were trying to discretize this setup, but that's because we have this notion in the discrete case, but that's what we don't know how to do. Yeah. So of course there are other relations, and okay, some integrable system will appear later. It will be an elliptic billiard. Yeah. So billiards. An ellipsoid will appear here, yeah. So, but nothing on an ellipsoid, yeah. No integrable systems on ellipsoid. Okay.
Thank you.
Okay. So now, okay, now I jump again, and we will do some geometry. So to the left, you see an example of incircular net, so IC net. As I have defined it, you have congruence of straight lines with combinatorics of the square grid, and every quadrilateral, which is generated by these neighboring lines, has an inscribed circle. So these circles, they are just inscribed, they don't necessarily have the same touching points. That's what you see here. Now look at the picture to the right. You see that here you have a checkerboard net. The same combinatorics.
Sasha, excuse me, I just.
Yeah.
There are special case of these nets similar to Darbur-Yegorov coordinate system, when actually it's not just opposite angles in these quadrilaterals are pairs, are orthogonal. Is there anything special subclass of this conformal quadrics? Or? You see, all orthogonal system of coordinates is Darbur metrics, right?
Yeah.
There is special potential case, Yegorov-Darbur.
Yeah, I know. So there is nice discretization, of course, yeah? So when you have two opposite orthogonal 90-degree angles,
yes.
Yeah.
But
so the question is whether there are quadrics, confocal quadrics in this class with this property.
Yes, all of this.
I think we looked at this, but I don't remember. I don't remember right now. Yeah.
Probably the answer, there are no such.
Maybe, yeah. So maybe it's too restrictive. Yeah. Okay. I don't remember again. Don't remember. So
no, it's too restrictive. In the continuous case, this is a special subclass. Of course, under discretization, it should be transformed to something different.
So I think what would be natural to look at here, yeah. So we have this orthogonality condition, which I have explained. In addition to this, and that's the definition of an orthogonal coordinate system, yeah. So and then additionally, you may assume that it is Yegorov in the sense that all the quadrilaterals have pair of 90-degree opposite angles.
Oh, 90 degrees probably is too restrictive. No, but some kind of general discrete version of Yegorov condition.
Well, it's a discrete version of Yegorov condition, yeah. So two 90-degree angles, yeah. So I don't think it's too restrictive. It looks fine, yeah. So, but okay, that will be a different class of orthogonal coordinate systems, yeah. So, okay, now we are going a little bit away from confocal coordinate systems, and we are doing checkerboard IC nets. So we will do a little bit geometry. You see, to the right we have the same combinatorics of straight lines, and but only one half of quadrilaterals have inscribed angles, circles. Excuse me. So, and these are called checkerboard IC nets. I will explain you why it's natural to consider such nets. So first of all, one incidence theorem, quite elementary. If in this picture you see 3 circles and how many? 6 lines, right? So, and it turns out that as soon as you have this picture, all 6 lines are tangent to a conic. I remind you that the conic is determined by 5 touching lines or 5 points lying on the conic. The 6th one is already an incidence. And moreover, if 2 of the circles exist in this picture, then the 3rd one also exists. And now, what's the difference and what is an advantage of this checkerboard IC nets? So you can observe that checkerboard IC nets belong to Laguerre geometry. And this means that, first of all, you can orient all the lines and all the circles in such a way that they are in oriented contact. You see, these orientations are shown here, and you can easily check that they agree everywhere. And you see also that you cannot fill the empty quadrilaterals here with circles in such a way that the orientation will be consistent. Yeah, so in such a way that they will be in oriented contact. For IC nets, it's impossible. For checkerboard IC nets, it's possible to orient the circles and to orient the lines in such a way that they are in contact, in oriented contact. And this is lines and circles, oriented circles, and exactly this oriented contact are studied in terms of in frames of Laguerre geometry, which is not a popular geometry, but maybe some of you haven't heard about this geometry, and I will just make an analogy of this geometry to Möbius geometry, which is much more popular. So,
can you explain what is Laguerre geometry is?
Well, I'm trying to do this, yeah. But first of all, look. In Möbius geometry, you have circles in the plane. You have circles and you have points. And you have an incidence. A point lies on the circle. And you have a group of Möbius transformations. And this group of Möbius transformations map circles to circles. And that's why you say I'm doing Möbius geometry. And moreover, you have some invariance. For example, if 2 circles intersect with some angle, then this angle is preserved after a Möbius transformation. So here, Laguerre geometry, in a way, is similar to Möbius geometry, but instead of points, you have lines. Yeah, you don't have points in Laguerre geometry. You have circles and you have lines. And instead of saying a point lies on a circle, you say my circles and my lines are oriented and they are in oriented contact. Therefore, what we see here, this checkerboards I see net, is a perfect subject, perfect topic in Laguerre geometry. So I'm not going to teach you Laguerre geometry, but I will maybe later say a few words about this. Yeah? So I want to say that it's a natural setup, natural class of incircular nets to be studied, yeah, because it's what can be studied in frames of some natural geometry. And here in this slide, you see also an incidence theorem. Okay, this picture looks quite symmetric, and all the squares are squares and they are all equal, but imagine this is not the case. And you have these black lines, forget about red and blue lines at the moment, and you have inscribed circles. All but one, yeah? So the last one, this 13th circle, doesn't exist. So you don't know whether it exists or not. And the claim is, if these 12 circles exist, then the last one exists as well. This is a new incidence theorem, and maybe...
Why it's 13?
Well, just count.
No, I see. But what is special about 13 in this geometry?
Yeah. So, okay. Well, maybe
is there some intrinsic explanation of this number?
Well, there is, of course, yeah. So I prepared an explanation of this picture in frames of Laguerre geometry. So if we will come to this, I will be happy to explain this, yeah. Okay, but maybe for now, just maybe I will try to convince you that this is true, that this incidence theorem is true. Okay, and then I will share you another screen with you, another frame. Okay, hopefully this will work. Okay. Okay, so look what happens, yeah? Can you see the picture?
Yes.
Okay. So that's the way how you can sort of prove incidence theorems nowadays, yeah? So at least when you see this, yeah, you have no doubts that it's true, and then you start to prove this, yeah?
But you need to know.
Yeah, of course. You come to, yeah, of course, yeah. First you should conjecture this, yeah. And this is a difficult thing, yeah. Okay, so that's the claim. And now I will stop to share this frame and come back to my slides, yeah. Okay. And now let us look how it works, yeah? And we play the same game, yeah? But with half of circles, okay? Much more parameters, yeah? So 4 parameters here, yeah? 4 circles, and every circle can be scaled, yeah? But now these lines are fixed. And I'm trying to explain you what kind of incidence theorems you should have here, and how one can come to this 5 times 5 incidence theorem. So now these circles are uniquely determined by the tangency conditions. So this circle is, well, you can change size, but as soon as you have chosen one, you have these lines. And all the choices here I'm making, I should say, are arbitrary, yeah? So there are no requirements. So now these 2 are fixed, these 2 lines are fixed, and then now you have a conjecture that the last corner here has an inscribed circle. And this is indeed true. This is exactly the incidence theorem I told you about. And that's it in one more visualization. This is the main incidence theorem. And as soon as you have this, you can proceed further, yeah? In the same way, applying this incidence theorem again and again, again and again. And that's how it works, right? Okay. So now, what about the integration? Okay, so let me say maybe a few words again about Laguerre geometry. So I will make some claims and I will not be able to prove them now. First of all, one can consider all the lines you see here, this 5 times 5 incidence theorem, but then you have how many lines? 12 lines. And they all can be tangent to a conic. And if they are tangent to a conic, then we have a special subclass of checkerboard IC-net. And this is very closely related to our original incircular nets. Essentially, by doing this subdivision or rep subdivision step, I have presented to you with 3 circles. And since we are doing this in frame of Laguerre geometry, there are also Laguerre transformations, and you should think about them as about analogs of Möbius transformations we had in Möbius geometry. We take this picture and apply a Laguerre transformation. This Laguerre transformation maps straight lines to straight lines. It maps circles to circles. It preserves the oriented contact, but the picture changes and there is no confocal conic anymore. The curve becomes more complicated. And that's the case of general checkerboard IC nets. So the way how we solve them all and how we find formulas for them in terms of elliptic functions for all these checkerboard incircular nets is that we solve first the case when the lines are tangent to a conic, and then we use this observation that the general checkerboard IC net is just a Laguerre transform of confocal checkerboard. So now, since I have said already many not quite understandable maybe claims about this Laguerre geometry, maybe let me spend 5 or maybe 7 minutes on Laguerre geometry and explain you what is going on. So what are natural objects in this Laguerre geometry? As I said, they are oriented lines and circles. And lines are even more important than circles because lines are, as I said, are analogs of points in our Möbius geometry. Yeah, to the right, you see lines and circles in oriented contact. We are in the plane, and every line is given by 2 numbers. V is the direction vector for this line, which is on the unit circle because it's normalized, and d is the distance from the origin. So, and this is arbitrary real. So as soon as you have v and d, you have vt plus d equal to 0, and this is, well, vt plus d, and this is your oriented line. S1 times r is a cylinder, and that's the cylinder which is shown here to the right. The points on this cylinder are our oriented lines. So L1 and L2, these 2 lines to the right we see as lines in the plane. In our cylinder are just 2 points. And this cylinder consists of oriented lines in 2-dimensional space. Now, if we have 2 lines, then we can draw a line, here L, shown in red, Or what we can do, we can construct one parameter family of circles touching these lines. Yeah? And these circles that are in oriented contact with two lines, shown in green to the right. In the right picture, in the left picture, are represented by planes containing the line, the red line. So you rotate this plane along the line L, about the line L, and all these planes correspond to circles, to green circles. That's the picture which visualizes us lines and circles in Laguerre geometry. And, yeah?
Say it again. How you, what's the relation between the plane and the circle? Because there are two one parametric families of objects.
That's right. That's right. Yeah. So you have okay. These circles will appear in a moment. Yeah. Yeah. So well, actually, I haven't explained which circle corresponds to which plane.
Yeah? Yes.
So
yes, exactly what I am asking.
Yeah. Yeah. But if you have a plane, it gives you a circle in this. Is
it just in this parameterization intersection of the plane with a cylinder?
Yeah, exactly. So you have you take a plane, you intersect it with a cylinder. You have this point.
It's not obvious. It's not obvious that you get a circle.
It's not obvious, but it's true. Yeah. So you have plenty of lines, and they will be tangent to this circle. Okay. Okay. Now we have this picture, and now I will show you this picture in Laguerre geometry. You see there are other lines that are shown in red and in blue here. And these lines, for example, this line L1, it corresponds to one parameter family of circles touching two lines, L1 and L2. And you have blue lines and you have red lines. So now I have erased all the black lines that were original lines in our plane, and have drawn all the blue and red lines. And I remind you, these were families of circles that are tangent to these two lines. So these lines become exactly the lines intersecting our Blaschke cylinder. And they are shown here to the right with the Blaschke cylinder. And you have this incidence construction. You have this incidence occasion here. Yeah. So blue lines intersect. This means that this blue line, corresponding to this one parameter family of circles touching L1 and L2, intersects with the blue line corresponding to blue line M1, corresponding to one parameter family of circles touching the lines M1 and M2, because they have a common touching circle, this circle S1. This circle S1 is the intersection point of the blue lines L1 and M1. And maybe I will not go to further details here, but what you can see here, that you have families of intersecting lines. And we are in three-dimensional space. So, and if you have three lines intersected by three lines like this, this means that you have a hyperboloid. Yeah? So there is a red and blue hyperboloid. They intersect our Blaschke cylinder along the same curve. And this is the occasion when you say, okay, these three quadrics, two hyperboloids in the Blaschke cylinder, build a pencil, and then you use this to prove this incidence theorem. And I don't have time really to prove this. Yeah.
Sir, just historic question. The other incidence theorem, they were known since Menelai or something like that.
Yeah.
This is new one. It was not known to classical geometry, or it was.
It seems to be a new one. Yeah. So, and in Laguerre geometry, you know, what is it was obtained in our paper with Jacobi. Yeah, so the 5 times 5 incidence theorem. And in Laguerre geometry, what is attractive about these incidence theorems? That you can have it embedded. Yeah. So usually in projective geometry, when we have an incidence theorem, it's an overlapping of many lines and many incidences, and then you should really spend some time on trying to understand what is going on. Here, the picture is as simple as this one. Okay, and now I will show you several cases. So what are the corresponding quadrics and how do they intersect the Blaschke cylinder? This is one possible way of intersection, and the corresponding, that's a question about the signature. Yeah? So how many component the intersection curve of such a hyperboloid and the Blaschke cylinder has. So in this picture, you see there are 2 components of this intersection curve. In this picture, there are also 2 components which you see, but they're vertical. Yeah, so something like this. Yeah? So, and there are several locations, and then you can obtain either IC nets associated to ellipses or to hyperbolas. Okay, and then one more picture about IC nets and about confocal checkerboard IC nets. So all the lines are tangent to conic. Now maybe, and that's the case with all lines that are tangent to hyperbola. Okay, now let me spend just a few minutes on possible generalizations, which I would like to mention, and that's forthcoming research or some research we did. So look,
Serge,
yeah.
In the usual case, when you have just IC net, the factorization property plus orthogonality, that was characteristic for discrete quadrics, right?
Yeah, conics in this case.
Yeah, conics. In the checkerboard case, is there anything of that kind that certain factories? No. So no. You don't see conics, quadrics in checkerboards, I think.
Well, we do see them because we use them when we construct them explicitly. When we can describe them all explicitly. This all checkerboard IC nets, and when we do this, we first normalize them all by applying the appropriate Laguerre transformation to the case when all the lines are tangent to a conic. And this is the case when you have an IC net, not a checkerboard IC net, but an IC net. And then you have your confocal conics. But then you can solve the system in elliptic functions. And then you apply this Laguerre transformation back. And this is just a linear map in the ambient space. Yeah. So in the space where your Laguerre geometry lives. Yeah. In this case, it will be R211. Yeah. But I wanted to show you a couple of additional structures that appear in this setup. We see here an IC net with inscribed circles that are shown in violet. But also, you see that if you draw the lines through the centers of these circles, these are black lines. So the lines which we have seen previously are these dotted blue lines. But now we have also, of course, we have also these black lines that pass through the centers of the circles. And then these lines, they built dual lattice, and they have quadrilaterals. You see what you can do. You can inscribe conics in these quadrilaterals. And of course, you can inscribe conic in any quadrilateral. And there is even one parameter family of conics that can be inscribed in a given quadrilateral. But what is special here is that the conics inscribed in these quadrilaterals, they have common touching points. So for example, if you see my mouse, I take this conic and choose it. Then the touching point is given to me. And I have this quadrilateral, the neighboring one, and I have 4 tangency conditions and 1 incidence condition that the conic must go through this point. And there are 5 conditions that determine me this conic uniquely. Then I pass to the next quadrilateral and go around this vertex this way. And for this last quadrilateral, the conic is uniquely determined already. And then it turns out that the last touching point will coincide with the starting touching point of my starting conic. Yeah? So if you go around the vertex, then this construction closes up. So there is a family of touching conics with common touching points. And actually, this is one parameter family. So which is shown here. And what one can do, I'm going now to projective geometry. There are no circles anymore, but there are already straight lines that are touching to a conic, and with a family of inscribed conics with common touching points. So that's, you see, I have forgotten my circles, and now that's a picture about conics. And then you ignore the conics, the circles, and it may happen that they don't exist. And actually, it's quite interesting how this case when the circles exist can be characterized in these geometric terms. Look here to this picture. We have blue and black lines. Black lines determine as quadrilaterals where the conics are inscribed. And blue lines, they pass through the touching points of our conics. So there is, in this one parameter family of touching conics, there is one occasion when these points lie on lines. Blue lines intersect our ellipse, and black lines are tangent to our ellipse. And then what you see here, you see such a trajectory in ellipse, the blue one. Yeah. So, and at every point of our trajectory, I have a touching black line. And this trajectory is an elliptic billiard if and only if I have my family of circles. So this is a special case. And in projective geometry, what I can do, I can start with any trajectory, build the tangent lines, and extend it in this way as it is shown here. But then the circles will not exist. Okay, so if I play a billiard with this canonical reflection law, then it's the case with circles. That's one generalization. Yeah.
This is elliptic billiard with periodicity condition?
Not necessarily. Not necessarily. In this case, it is periodic, but of course, it's local construction. So there is no need for periodicity. Okay, so that's generalization to direction of projective geometry. Now a generalization, so you can consider incircular nets in hyperbolic space and on the sphere. So here you see it's a different story. It's Laguerre geometry in hyperbolic space and on a sphere, which was not developed classically, but now it is developed. And you see here in this picture that all black lines intersect the equator of the sphere orthogonally. And this means that the half sphere, the upper half sphere here, is our hyperbolic space, the conformal model, half sphere model of our hyperbolic space, and the black lines are geodesics in this hyperbolic space. And since the model is conformal, circles are circles. So that's what you have here. The quadrilaterals, they look differently. They have inscribed circles, and all black lines are geodesics here. And the orange line here is conic in our hyperbolic space. So that's a different representation for the same picture. Yeah, so now it's a conformal model of the hyperbolic space. And this picture is even simpler because it's the same story in the round sphere. Now the geodesics are big circles on the sphere, and they also separate our sphere in quadrilaterals in such a way that these quadrilaterals possess inscribed circles. And again, you have this now conic defined on the sphere. Okay, so now we are coming to applications. So that's next visualization of an IC net on a sphere now as a sculpture. So I wanted to show you maybe one more application of discrete confocal conics in jewelry. And maybe I will finish my talk with one more movie of showing how one can decorate palaces using mathematics. Then the pictures are slightly different comparing to the pictures we have seen in TV, yeah, recently, yeah. So share screen. So now that's the picture. Okay, and let me show you 1 minute movie with confocal discrete IC nets. Yeah. There is no music, but incidence theorems are implemented to make all this. Yeah. Mm-hmm.
It exists in nature, or it's just drawings?
It's virtual, yeah. So, but we are thinking maybe we should build a startup to do this, yeah, to produce this, yeah. So, of course, it's virtual reality, yeah. But I think it's quite practical because you have non-trivial patterns, and I think they are beautiful, and they can be built out of Eisen, yeah, or iron, yeah. I mean, okay. Okay, so that I think the end of my talk and the end of this final entertainment. Yeah. So thank you very much for your attention. Yeah. Okay.
Thank you, Sasha. I have a lot of questions, but probably I'll ask him them later.
Yeah. You've asked already many questions. Yeah.
Any questions, comments? Then just
Well, maybe I will ask, there was term integrable systems or something like this is a title, but what do you call integrable systems here? How to, I have to check.
Okay, so here it was really an integrable system, which was used originally. This equation I have written, and together with factorizability properties, the solution of this equation correspond to discrete confocal coordinate system. Yeah, that was the first way how we came to this discretization. But geometrically, when we are thinking about integrability, then we prefer to think about discrete integrability. And this means usually that we are working with multi-dimensional grids. And in any coordinate direction, you have the same equation that is responsible for this lattice. And all of them, they must be consistent in a way that they define as a multi-dimensional grid. So we had many occasions like this. It leads to three-dimensional to two-dimensional integrable systems. So here, you shouldn't expect to get a three or two-dimensional integrable system, because I was talking about confocal quadrics, and you have a finite dimensional set. Yeah. So, or a set which depends actually on one parameter. Yeah. So, but how one can come to this? You start with an integrable system which is multidimensional, which is consistent, and then you are looking for some special solutions to this integrable systems. In this case, factorizable.
Okay. Okay.
Sasha, this incidence theorem, are there some kind of compatibility or condition of some linear systems? Can they be treated in this way?
I'm not sure. Yeah, so that's what should. So here they are maybe on the level of one-dimensional systems in a way. Yeah. So the whole stuff we are investigating here, it depends on finitely many parameters. Yeah. So I don't see here really this compatibility, this incidence theorem as sort of Lax equation or whatever. Yeah. So it's maybe on a little bit more basic level. Yeah.
More questions? Then just thanks, Sasha. And
okay. Thank you all. Yeah, it was a pleasure to be virtually in Russia, to be with you. Okay.
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 Bye.
Bye-bye. Thank you.
Thanks.